On June 4, 2026, a thermal camera near Area 51 recorded something impossible. The aircraft carried no tail, no visible flaps, and no cockpit. Defense analysts immediately linked the shape to America's next-generation fighter program. But the real story isn't the airframe itself. It's the technology that lets a plane turn and climb without moving a single surface. Groom Lake remains the graveyard of secrets for American military aviation. The U-2 spy plane first flew there in the 1950s. The SR-71 Blackbird and the F-117 Nighthawk both spent years in the skies above that same restricted desert basin, long before the public knew they existed. That history meant the defense community paid attention when thermal cameras picked up an unknown shape in early June 2026. The footage first surfaced on June 4th through aviation observers who monitored the restricted airspace around the test range. That imagery showed a single aircraft in night flight, captured in infrared against the cold Nevada desert floor. The shape stood out immediately because it lacked every surface Americans expect to see on a modern fighter jet, from stabilizers to control surfaces, and the wings swept back in a cranked kite planform with two small Canard foreplanes forward of the main wing. Nothing in the current U.S. inventory matches that silhouette. The aviationists published the imagery before most other defense outlets. Their analysis noted that the thermal signature indicated a single airframe under power. The aircraft appeared to be conducting a low-speed pass or a landing approach, which meant it was either a prototype or a full-scale technology demonstrator. And that behavior matters because Black Project aircraft rarely fly in conditions where amateur sensors can capture them. For decades, sightings like this have preceded every major Black Project reveal. The U-2 created the original UFO wave over the desert in 1955, and the F-117 generated thousands of false reports before the government declassified its existence. Yet the pattern remains unmistakable, and it has repeated with nearly every secret aircraft that America has ever tested. When something unknown flies over Area 51, the rest of the world usually finds out about it 5 to 10 years later. The shape caught on thermal footage isn't random. It's a tailless, cranked kite wing with forward canards, a configuration that defense analysts immediately recognized and linked to the Boeing F-47. President Trump announced that aircraft on March 21, 2025. The F-47 will replace the F-22 Raptor, and it's the first sixth-generation fighter program ever to reach the engineering and manufacturing development phase. Boeing won the contract after years of secret competition against Lockheed Martin. The aircraft will carry advanced stealth, artificial intelligence-assisted combat systems, and the ability to command autonomous drone wingmen. Yet the shape in the Nevada sky raised an immediate problem. Canards are small control surfaces mounted ahead of the main wing. They improve maneuverability and low-speed handling, but they create frontal radar reflections that most stealth engineers try to eliminate. The F-22 and the F-35 both avoid canards for exactly that reason, which explains why analysts were surprised to see them on a Black Project test article, and either the stealth technology has advanced beyond the need for pure shape optimization, or the aircraft in the footage isn't the final F-47 design configuration. Both possibilities point to a different breakthrough, and that's where the real story begins. The war zone warned that many questions remain. The outlet warned that the aircraft could be a subscale demonstrator, a full-scale mock-up, or an early prototype that will change shape before it enters active production. Until Boeing or the Air Force releases an official image, every analysis remains educated speculation. Yet the F-47 might not be the only program flying over Nevada. Since 2020, DARPA has been running a separate initiative that remains just as radical, and it's called CRANE, which stands for Control of Revolutionary Aircraft with Novel Effectors. The goal isn't to build a fighter. It's to prove an aircraft can fly and maneuver without any moving external surfaces. Aurora Flight Sciences, a Boeing subsidiary, won the contract to build the demonstrator. The aircraft carries the designation X-65, and it's subsonic, unmanned, and weighs over 7,000 pounds with a 30-foot wingspan that makes it smaller than most tactical jets, but large enough to test full-scale aerodynamic principles. Every number in that description looks modest, which means the real surprise comes from what designers built the X-65 to do. It'll turn, climb, and descend using a system that has no flaps, no rudders, and no ailerons. DARPA spent $38.2 million on the program in fiscal year 2024 and another $23.8 million in fiscal year 2025, which means the total visible investment sits at over $60 million. That isn't a classified black budget. That's less than one F-35, and it could change how every future aircraft is built. Aurora hasn't hidden the X-65 in a vault because the company published photographs of the airframe under assembly, and the program is real, it's funded, and 2027 marks the first flight. Yet few people outside the defense industry have ever heard of it. This isn't a conspiracy theory. It's a DARPA program with a public budget and a named contractor, and it's preparing for a first flight in 2027 that will test something no previous aircraft has ever attempted before. In 1903, the Wright brothers flew at Kitty Hawk, and every powered aircraft since then has used the same method to turn and control its flight, from the wing warping of the first flyer to modern flaps and ailerons. Those surfaces physically move to redirect airflow and change the aircraft's attitude, a principle that has governed aviation for over 120 years. The X-65 does none of that. Instead, the demonstrator uses a technology called active flow control. It relies on 14 banks of fixed actuators embedded in the wing and tail surfaces, and each bank blasts precise jets of air that create lift and directional forces. Think of it like steering a boat with water jets instead of a traditional rudder, because the hull stays fixed while the thrust changes direction. That's exactly how the X-65 will steer without rudders or flaps when it flies for the first time in 2027. The 14 actuator banks aren't placed randomly. They're positioned at specific points across the wing where airflow separation normally occurs during high-angle maneuvering, and by blasting air at those locations, the X-65 can create differential lift to produce roll, increase drag to yaw, or adjust camber to pitch up and down. All of this happens with fixed hardware. None of that is theoretical. DARPA and Aurora tested scaled models in wind tunnels before full-scale construction, and the fixed actuators weigh less than the hydraulic systems they replace. They remove every seam and gap that opens when a conventional flap extends, and on a stealth aircraft, those gaps become radar reflection points that an enemy sensor can exploit during takeoff, landing, or combat maneuvering. Active flow control turns on or off as needed. It adds energy to the airflow in a regulated manner that replaces the mechanical complexity of movable surfaces and leaves the aircraft with fewer parts to maintain and a lighter airframe overall. The catch is that the system requires pressurized air, which demands engine power and sophisticated control software. But DARPA has already solved harder problems with less funding. If the X-65 proves the concept in operational flight testing, the technology can scale to larger aircraft that operate in contested airspace without the stealth penalties of traditional moving parts. The advantages go beyond maintenance. On a conventional stealth fighter, the pilot controls the aircraft by extending flaps, rudders, and ailerons, and every time one of those surfaces moves, it opens a gap in the airframe that reflects radar energy. It's a temporary breach in the aircraft's invisible cloak that happens during combat maneuvering, takeoff, and landing. A surface-free aircraft doesn't have that problem. The outer mold line stays exactly the same during a gentle turn or a hard evasive pull, because there are no hinges to flex and no edges for enemy radar, and the radar cross-section remains consistent across the entire flight envelope, which is something no current operational fighter can promise. That consistency explains why a tailless, surface-free design appeals to engineers who want to push stealth beyond current coatings and shaping. That leads to how modern stealth actually works, because both techniques work well when the aircraft is in straight and level flight. But the moment a pilot banks hard or deploys landing gear, the geometry changes and the signature spikes in ways that ground-based radar can exploit. Active flow control removes that variable entirely because the outer surface never changes shape. That's the ghost advantage. The aircraft never exposes itself because it never changes shape. The weight savings are also real. Hydraulic actuators and backup mechanical systems add hundreds of pounds to a fighter's empty weight, and removing them frees up mass for fuel, weapons, or sensors that increase lethality without increasing radar signature. The X-65 is only a subsonic demonstrator, but the physics scale. A full-scale sixth-generation fighter that uses active flow control could operate at longer range, carry heavier payloads, and survive in airspace that would force a conventional aircraft to run its control surfaces wide open. The path from DARPA experiment to operational black project has been traveled many times. The U-2 started as an experimental reconnaissance concept before it became the CIA's highest altitude spy plane. And the F-117 began as Have Blue, a technology demonstrator that proved stealth shaping could work. Have Blue crashed twice, but the data it generated led directly to the F-117 production line. The RQ-170 Sentinel flew for years in secret before anyone outside the Pentagon knew. And in every case, engineers tested the technology openly before it disappeared into classified programs. And that points to the timeline, because Aurora plans the first X-65 flight for 2027. But the Area 51 sighting happened in 2026, which means that one-year gap rules out nothing. Black project history shows that the most important flights stay off public schedules. DARPA programs often spawn operational test articles that fly years ahead of the acknowledged schedule. And if the X-65 technology has matured faster than public timelines suggest, the aircraft over Nevada could be an integrated test bed, combining this technology with a larger combat airframe. That leads to what the F-47 is actually supposed to do, because the Air Force expects the F-47 to operate as a command node for collaborative combat aircraft, which are autonomous drone wingmen that carry weapons and sensors under a crewed leader. A tailless, surface-free design fits that role perfectly. It could penetrate contested airspace without the radar spikes of a conventional fighter, direct multiple drones simultaneously, and return without ever exposing the control surfaces that betray most stealth platforms. Boeing hasn't confirmed the F-47 uses this system, and DARPA doesn't discuss operational transitions. That isn't confirmed, but it's exactly what you'd build if you had the technology and the budget to field a next-generation combat aircraft that could dominate contested airspace without relying on conventional moving surfaces. The United States isn't the only country building a sixth-generation fighter. China has been flight testing its own design for years, and Russia has announced plans to field a successor to the Su-57, which means both programs aim to close the gap that American stealth technology opened in the 1990s. Neither country has confirmed it's testing the same approach, which means the technology stays an American advantage only if engineers mature it first. And that creates the problem. In 2011, Boeing built its last F-22 Raptor after only 187 aircraft, and that number remains so small that senior Air Force officers call it a strategic liability. 187 aircraft isn't a fleet, and it's a liability that still wears stealth coatings. The F-35 Lightning II is a capable multi-role fighter, but designers didn't build it to win air superiority battles against peer adversaries, because it's a workhorse and not a thoroughbred. That leads to why the F-47 matters. America needs the F-47 to restore the edge. Active flow control isn't a minor upgrade because it's a qualitative change in what an aircraft can do, and a fighter that never changes shape can survive longer in denied airspace and coordinate with autonomous wingmen without exposing itself. Reverse engineering that capability would require an adversary to replicate the embedded actuator software and the thousands of hours of flight test data needed to make it reliable. China has been flight testing its own next-generation design for years. The program appears to be building toward an operational sixth-generation fighter that could enter service by the early 2030s, and that timeline pressures the American programs. If the F-47 program slips, or if active flow control fails to transition from the X-65 to an operational platform, the United States could find itself with a numerical and technological disadvantage in the Pacific. The Ghost Jet isn't science fiction. It's the next era of American air power being written in Nevada desert air. And while you're still here, click the link on your screen for another Black Project breakdown with more programs we can't cover here. Whatever is flying over Groom Lake tonight, the sky above it will never look the same. On May 8, 2026, the U.S. government released classified UFO files that confirm what researchers have been saying for decades. Not grainy footage, not pilot testimonies that get dismissed at press briefings. Actual program documents from inside the U.S. intelligence apparatus confirming that non-human craft have been recovered. But here's what the headlines are missing. The real story isn't that UFOs are real. It's that the U.S. has had them for decades, handed them to defense contractors, and has been quietly learning how to fly them. The release covers documents spanning multiple agencies, including the Defense Intelligence Agency, the Office of Naval Intelligence, and several programs that had no public name until this month. What makes this different from every prior disclosure is the language. Previous releases talked about unidentified aerial phenomena in careful, detached terms. These documents use phrases like recovered non-human origin craft and material of non-terrestrial manufacture. That's not bureaucratic hedging, that's an admission. The scope of what dropped in May is wide, but it's the gaps that tell the deeper story. Whole sections are redacted. Specific program names appear once and then disappear behind black bars for the next 30 pages. You can see the shape of something much larger being deliberately kept out of frame. Several documents reference programs that connect directly to known black budget operations. The names won't be familiar to most people, but defense researchers have been tracking anomalous budget line items for years. Money that flows into programs with no public description and no congressional oversight record. What the May 8th files do is start filling in what some of that money was actually for. So why release any of this now? The answer is congressional pressure that's been building since 2023, combined with whistleblower protection legislation that made it legally safer for insiders to come forward. The UAP Disclosure Act forced the hand of agencies that would have sat on this indefinitely. Multiple former program officials had already testified under oath to the Senate Armed Services Committee that recovery programs existed. Once that's on the congressional record, full suppression becomes harder to maintain. Then there's AARO, the All-Domain Anomaly Resolution Office, which was set up in 2022 and spent 2 years publicly stating there was no evidence of recovered craft or reverse engineering programs. The May 8th documents directly contradict that position. Reports from inside AARO's own analysis chain reference material studies and propulsion research that don't match anything in the known aerospace inventory. The office was telling Congress one thing while its own classified reporting said something else entirely. One document that's getting a lot of attention references a program structure described as a tiered controlled access program, meaning it's classified above top secret in a way that legally exempts it from standard congressional oversight. That structure is how you hide something for 50 years without a single budget hearing exposing it. The program isn't in the black budget because it technically doesn't exist inside the normal classification architecture. It exists in a separate layer that most of the government can't even ask about. What's confirmed in the files, taken together, is this. Craft of non-human origin were recovered. Materials from those craft were transferred to contractors for analysis, and at least some of that work involved propulsion systems that don't match any known physics framework. The documents don't explain how far that work progressed, but they confirm it happened, and they confirm it's been happening for a long time. The files confirm recovery. But recovery is only the beginning of this story. What the U.S. did with what it found, who did the work, and what they've actually built from it, that's what the next layer of documents starts to reveal. If you wanted to hide the most advanced aerospace program in human history, Lockheed's Skunk Works facility in Palmdale, California, is exactly where you'd put it. This is the same operation that built the U-2 spy plane in total secrecy during the 1950s, then followed it with the SR-71 Blackbird, which flew so fast and so high that nothing could touch it. Then came the F-117, the world's first operational stealth aircraft, which the Air Force publicly denied existed for years while it was already flying combat missions. Skunk Works doesn't just build classified aircraft, it builds things the rest of the world won't believe are possible until they're already obsolete. The May 8th files reference contractor involvement in material analysis going back decades. Lockheed is named in connection with propulsion research tied to recovered craft, and the language used isn't vague. One document describes a materials transfer to a cleared defense contractor facility for analysis of non-conventional propulsion elements. Skunk Works has the clearance infrastructure, the physical security, and the engineering depth to run exactly that kind of program without a single public trace. Raytheon's role is different, but just as telling. Where Lockheed is about airframes and propulsion, Raytheon specializes in the sensor and weapon systems that would need to interface with whatever gets built. Their classified divisions have been working on directed energy weapons and advanced electromagnetic systems for years, and several of those programs have budget lines that dwarf their known output. If you're reverse engineering a craft that manipulates electromagnetic fields for propulsion, you need Raytheon-level expertise to understand what you're actually measuring. Their involvement points to a program that's moved well past basic materials analysis into something that requires operational hardware. The structure that makes all of this legally possible is called a Controlled Access Program, or CAP. It sits above top secret clearance and operates outside the standard congressional budget review process. A program inside a CAP doesn't appear in defense appropriations hearings. It doesn't get reviewed by the Armed Services Committee. The people running it can legally tell senators it doesn't exist, because inside the classification framework, it technically doesn't. This is how you spend decades and billions of dollars on something with no public record. The money moves through layers of contractor sub-accounting that were specifically designed to be untraceable. Bob Lazar described this exact architecture in 1989. He said he worked at a facility near Area 51 called S4, where 9 recovered craft were stored and studied. He described a propulsion system built around a stable isotope of element 115, which he called moscovium, that generated a gravitational field used for propulsion. At the time, element 115 didn't officially exist on the periodic table. It was synthesized and confirmed in 2003. Lazar's technical descriptions were specific enough and accurate enough on points that couldn't have been guessed, that dismissing him as a fraud requires ignoring a lot of inconvenient detail. The May 8th files don't mention him by name, but the propulsion research they reference lines up with what he described 37 years ago. Where does the money come from? Defense analysts who track black budget allocations have flagged a category of aerospace spending that's grown by roughly 300% since the early 2000s, with no corresponding increase in known program output, no new aircraft, no announced propulsion contracts, no patents filed. That money went somewhere, and based on what the files released describe, the answer is becoming harder to argue with. Start with what Navy pilots actually recorded, because that's where the physics breaks down in a way you can't explain away. The Tic Tac incident from 2004 gave us something rare: military sensor data, trained observers, and a craft that performed maneuvers no known aircraft can execute. Commander David Fravor watched it drop from 80,000 feet to sea level in under a second, stop dead, then accelerate in a completely different direction with no transition, no arc, no deceleration curve. Just an instantaneous change of vector at speeds that would reduce a human pilot to a stain on the seat. The G-force involved in that kind of movement, by any conventional physics calculation, would be somewhere between 400 and 700 Gs. A human body starts losing consciousness around 9 Gs. Whatever was inside that craft, if anything was, it wasn't being subjected to the same forces the airframe was generating. That's the first thing that separates these craft from everything else. They don't appear to be affected by inertia. When your car accelerates, you feel it push you back into the seat because your body has mass and resists the change in motion. These craft move as if that relationship between mass and acceleration has been switched off. The engineering community's best working theory is electromagnetic field manipulation, where the craft generates a localized field that essentially warps the space it's moving through, so the craft and everything inside it moves together without experiencing the directional forces that would normally apply. You're not pushing through space, you're moving the space around you. Then there's the propulsion signature, or more accurately, the complete absence of one. Every aircraft ever built leaves traces: heat bloom from engines, exhaust gases, a pressure wave that generates a sonic boom above the speed of sound. These craft produce none of that. Radar tracks them at speeds well above Mach 1 with no sonic signature. Infrared sensors find no heat output. There's no jet wash, no plasma trail, nothing that conventional propulsion would leave behind. Whatever is moving them isn't burning anything and isn't pushing against the air. The altitude performance compounds this, from a standing hover at low altitude to above 80,000 feet in a matter of seconds, with no acceleration phase, no engine spool-up, no detectable thrust vector. That's not improved propulsion, that's a different category of physics entirely. Stealth properties add another layer. These craft don't just absorb radar the way an F-22 does with its angled surfaces and radar-absorbing materials. They disappear from multiple sensor types simultaneously. Radar, infrared, optical tracking, all go blank at the same moment. That kind of cross-spectrum disappearance suggests the craft can manipulate its own electromagnetic signature across every detection wavelength at once, not just deflect one type of sensor. Now factor in the TR-3B, a triangular craft reported independently by dozens of witnesses across multiple countries over the past 30 years, always described the same way. Silent, slow-moving at low altitude, capable of accelerating away at speeds that leave no trace on radar. The consistency of those descriptions across unconnected sources is hard to write off. If the reverse engineering programs described in the May 8th files produced a flying prototype, a triangular platform would be a logical airframe choice for a craft using field-based propulsion rather than conventional thrust. Even replicating 20% of what these craft can do would make the result invisible to every air defense system on the planet. No radar lock, no heat-seeking missile track, no intercept solution. If the US has crossed that threshold, the gap between American air power and every other nation isn't measured in generations. It's measured in physics. China's DFZF hypersonic glide vehicle tops out around Mach 10. Russia's Avangard system reaches Mach 27 under ideal conditions. Both represent years of development and genuine engineering achievement. They're also still moving through the atmosphere the same way a rock moves when you throw it, subject to drag, heat, gravity, and tracking solutions that improve every year. Western air defense systems have already started adapting to hypersonic threats. The physics is understood. The countermeasures are being built. A craft that produces no radar return, no heat signature, and no inertial profile isn't a faster version of the same problem. It's a problem that existing defense architecture has no answer for, because every detection and intercept system ever built assumes the target is operating inside Newtonian physics. You can't compute an intercept solution for something that changes direction instantaneously. You can't guide a missile to a heat source that doesn't exist. You can't jam a craft that's already invisible to every wavelength you're transmitting. That's what makes the strategic gap here different from any prior technology advantage. When the US fielded the F-117, it took years before adversaries developed radar systems capable of tracking low observable aircraft. Eventually they did. The physics was still the same, just harder to work with. What the May 8th files point toward is a capability that doesn't give adversaries a longer timeline to adapt. It gives them no pathway at all, because the underlying physics isn't an evolution of what they already understand. The surveillance applications alone would reshape geopolitics entirely. A platform that can reach any point on Earth undetected, loiter without any thermal or electromagnetic trace, and exit before any response is mounted gives the US an intelligence collection capability with no precedent. Every facility, every command structure, every weapons program a foreign government believes is hidden becomes visible, and they'd never know it happened. That's why this stayed buried for so long. Releasing it doesn't just trigger an arms race. It collapses the entire framework of mutual deterrence that international security has been built on since the 1950s. Every treaty negotiated under the assumption that both sides had roughly comparable detection and strike capabilities becomes meaningless. Every military alliance recalculates its value. The geopolitical order restructures overnight and not in ways anyone can fully predict. Lockheed and Raytheon aren't going to confirm any of this. The program managers who ran these operations signed agreements that don't expire and carry criminal consequences. But the May 8th documents are doing something those individuals can't stop. They're assembling the outline of a program that was never supposed to have an outline. Each redacted page still shows you where the edges are, and the edges are a lot larger than anyone outside this program was supposed to know. The US didn't just recover something, it spent decades turning that recovery into operational hardware, and the rest of the world is only now finding out that race was run without them. What dropped isn't the end of the story, it's the first time the story got official edges. The US has been flying ahead of the known world for decades, and the files are finally saying what the contractors never will. There's a hangar at RAF Wharton in Lancashire that doesn't get talked about much. No press tours, no open days, no carefully staged photo opportunities with politicians standing in front of something they clearly don't understand. Just a building, a lot of security, and work happening behind closed doors that most people will never hear about until it's too late to be surprised. Meanwhile, the defense world keeps its eyes locked on America, the F-47 NGAD, the B-21 Raider making its slow, deliberate public debut. The US runs the loudest program, so it gets the most attention, and Britain just keeps working. But something is being built on that side of the Atlantic that doesn't show up cleanly in parliamentary budget lines or BAE Systems press releases. Defense analysts who watch classified spending patterns have started asking questions about numbers that don't add up. Programs that don't map to anything officially acknowledged. A name that circulates in certain circles, Dark Eagle, attached to a variant of the Tempest program that goes well beyond what anyone has publicly admitted exists. By the end of this video, you'll understand why NATO's air power equation just shifted in a way that almost nobody saw coming. Russia and China have both been watching the Western alliance's next-generation programs closely. Neither of them expected Britain to be the wild card. Most people who've heard of the Tempest file, it's somewhere between the F-35 and a British vanity project. A next-gen fighter, sure, but probably derivative, probably dependent on American technology, probably a decade behind where it needs to be. That framing is wrong on almost every count. The Tempest isn't Britain's answer to the F-35. The F-35 is a fifth-generation aircraft. The Tempest is being built for a completely different threat environment, one where fifth-gen stealth alone isn't enough to survive contact with the systems Russia and China are currently fielding. This is a sixth-generation program, which means the comparison to the F-35 is roughly like comparing a smartphone to a rotary phone, because they both make calls. And it isn't a solo project. The Global Combat Air Program, GCAP, brings Japan and Italy in as full co-development partners, not junior contractors. Japan's participation in particular changes the strategic character of the whole program. You're not looking at a single nation building a capable fighter jet. You're looking at three technologically advanced nations pooling their most sensitive aerospace research into one platform, with a combined industrial base and a shared interest in not depending entirely on Washington for their high-end air combat capability. The publicly confirmed specs alone put it in a different category from anything currently flying. The Tempest is designed from the ground up to operate alongside autonomous, loyal wingman drones, controlling a small fleet of unmanned aircraft while simultaneously managing its own threat responses. The onboard AI isn't a feature added late in development. It's baked into the sensor fusion architecture at the foundation level, pulling from multiple data streams and building a battle space picture faster than any pilot could do manually. Directed energy weapons are part of the original design spec, not a future upgrade option. The power generation system was engineered to support high-energy laser systems from day one, which tells you something about how seriously the program takes what the threat environment looks like in 2035 and beyond. The stealth geometry is worth paying attention to too, because it's different from what the Americans do. U.S. low observable design, think the F-22 and F-35, prioritizes a fixed radar cross-section built into the physical shape of the airframe. BAE's approach for the Tempest leans toward what you'd call adaptive radar cross-section management. The aircraft's electronic systems actively manipulate how it appears to enemy radar rather than relying solely on shape to stay invisible. The distinction matters because fixed-shape stealth can be partially countered with the right radar frequency. Active signature management is a harder problem to solve on the threat side. So 6th Gen for the Tempest isn't primarily about being invisible. It's about owning the electromagnetic space around the aircraft, controlling what every radar and sensor in the battlespace can and can't see, and doing that dynamically while the mission is in progress. That's the public program, the version that shows up in parliamentary testimony and airshow renders and officially sanctioned briefings. There's another version that doesn't appear in any of that, and it's been running longer than most people realize. Black projects in the UK defense world aren't a conspiracy theory framing. They're a real procurement category with a paper trail, even if the paper is mostly redacted. The Ministry of Defense has a formal mechanism for classified development programs, where the budget disappears into a line item that tells Parliament almost nothing about what's actually being funded. Most people assume this is an American specialty. Skunk Works, Area 51, the whole mythology. Britain has been doing the same thing for decades, just more quietly. The clearest recent precedent is Tyrannus. BAE Systems ran a fully autonomous stealth combat drone program for years. Airframe, propulsion, avionics, weapons integration. Before anyone outside the classified program knew it had progressed beyond a design concept. When it finally surfaced publicly, it was already flying. The lessons from Tyrannus didn't vanish when the program wound down. They went somewhere into the next generation of thinking about how an autonomous, low-observable aircraft should actually behave in a contested airspace. That context matters when you start looking at what defense analysts have been flagging in the UK MOD's classified spending figures. There are anomalies. Budget allocations that are too large in scale to be upgrade programs for existing aircraft, and too structured in their year-on-year progression to be basic research spending, which tends to be more irregular. The numbers point toward a sustained, phased development effort on something specific. Nothing in the acknowledged program list accounts for them. This is where the Dark Eagle name enters the picture. It circulates in defense analyst circles, in the kind of conversations that happen at industry conferences and in specialist publications that don't make the general news cycle. Whether it's an official program designation, an internal nickname, or a label that attaches itself to the program from the outside, nobody who'd know for certain is saying. What the name gets attached to consistently are rumors about a Tempest variant running on a parallel track to the public GCAP timeline, with a capability set that goes beyond what the official program acknowledges. The rumored specifications are worth laying out carefully because some of them are plausible extensions of known development directions and some are harder to evaluate. On the plausible end, an internal weapons bay optimized for long-range standoff strikes, which fits with the broader 6th-gen design philosophy of keeping external stores off the airframe in high-threat environments. Avionics architecture that can operate fully disconnected from any external network, which is a direct answer to the reality that in a near-peer conflict, communication links get jammed or destroyed early. You want an aircraft that doesn't stop functioning when the network goes down. The hypersonic capability claim is the one that sits at the edge of what's currently verifiable. Hypersonic dash in certain flight regimes, not sustained cruise, appears in the same discussions. Given the propulsion work being done on the program, which we'll get into shortly, it's not physically impossible. But it's also the kind of claim that's easiest to attach to a program nobody can verify, so treat it accordingly. What's harder to dismiss is the timeline implication. If a parallel development track has been running since the early stages of the public Tempest program, the official 2035 service entry date for GCAP may describe when the acknowledged version reaches the RAF, not when something is already operational. Tyrannus was flying before anyone outside the program knew to ask whether it was flying. There's no structural reason the same approach couldn't be applied here. The capability choices inside this program stop making sense as pure engineering decisions once you lay them against the specific threats Britain is actually preparing to face. Britain's threat geography is not America's threat geography, and that difference drives almost every decision inside the Tempest program. The North Sea, the Arctic corridor, the Baltic approaches, these are not abstract strategic concepts for the RAF. They're operational realities. Russian long-range aviation probes, British air defense identification zones on a regular basis, the Kola Peninsula, sitting just across the Arctic from NATO's northern flank, hosts some of the densest concentrations of Russian air defense and strike capability on the planet. For American planners, a conflict in Europe is a power projection problem. For Britain, it's a home defense problem with a very short reaction window. Russia's S-500 system changed the calculus for every NATO air force that pays attention to what it can actually do. Unlike earlier generations of Russian surface-to-air missiles, the S-500 is designed to engage targets at extreme altitude and range, including aircraft flying the kind of high-fast profiles that used to provide a margin of safety. The follow-on S-550, focused specifically on hypersonic and space-based targets, pushes that envelope further. Current generation NATO fighters, including the F-35 in certain engagement scenarios, face a real survivability problem against these systems. The Tempest combination of adaptive signature management and electronic warfare capability is specifically architected to operate inside that threat envelope without relying on standoff range as a substitute for genuine survivability. Japan's role in GCAP isn't a diplomatic gesture or a cost-sharing arrangement dressed up as strategic partnership. Japan faces a threat that mirrors Britain's in its structure, even if the geography is completely different. Chinese air power has been expanding in range, capability, and aggression across the Western Pacific. The J-20 is operational, it's being produced at scale, and China has additional sixth-generation programs in development that Japanese defense planners track very closely. Buying American platforms gives Japan capable aircraft, but it doesn't give Japan the ability to shape the platform's development around its own specific operational requirements, and it creates a dependency that becomes a vulnerability the moment Washington's strategic priorities shift westward. A shared sixth-gen program built around a common architecture solves both problems at once. Britain gets the industrial and financial weight of two additional advanced partners. Japan gets a platform it co-owns, co-develops, and can evolve independently. Italy brings its own aerospace engineering depth and a Mediterranean operational perspective that matters for Southern NATO. None of them get that from an off-the-shelf American purchase. The Su-57 is flying with Russian units now. The J-20 is flying with Chinese units now. NATO's current inventory was largely designed and procured against a threat environment that existed 20 years ago. The alliance is heavily weighted toward U.S. platforms for any genuinely high-end air combat scenario, and that weight becomes a strategic liability if American attention and resources tilt decisively toward the Pacific, which is exactly what the current geopolitical trajectory suggests is coming. Britain's calculation is specific. A sixth-gen platform with a Black Project capability layer needs to reach operational status before the threat environment matures to the point where it can no longer be answered with an aircraft that's still in development. That's not pessimism about the timeline. It's the reason the timeline is what it is, and it's almost certainly why a parallel track exists at all. The technology being built into this airframe is where that urgency becomes most visible. Start with power. The Tempest's electrical generation system was sized, from the earliest design phase, to feed high-energy laser weapons. Not as a future option, not as a weight penalty the engineers would figure out later. It's load-bearing infrastructure baked into the architecture the same way a carrier's flight deck is built for aircraft, not adapted to them afterward. That decision alone tells you what the program office believes the next air war actually looks like. The AI system BAE has described publicly is worth understanding precisely because it gets mischaracterized a lot. The pilot doesn't hand control to a machine. The pilot sets intent, the target, the mission parameters, the acceptable risk envelope, and the aircraft executes the tactical responses faster than human reaction time allows. A missile launch detected at close range, an electronic attack requiring immediate countermeasures, a split-second maneuver decision in a high-threat environment. The aircraft handles those in the gap between the threat appearing and the pilot's hands moving. The human stays in command of the mission. The machine handles the physics. Propulsion is where the program gets genuinely interesting. The engine work, referenced in some open-source defense documents under the name Orpheus, is targeting a power-to-weight ratio that supports supercruise, sustained supersonic flight without afterburner. That matters for one specific reason. Afterburner produces a massive infrared signature that modern IR-guided missiles can track from long range. An aircraft that can cruise supersonically without lighting that signature is harder to engage with the weapon systems that currently threaten the fast jets most seriously. Whether the hypersonic dash capability in the Dark Eagle rumors connects to a derivative of this propulsion work, nobody outside the program is confirming. But the engineering direction points that way. Sensor fusion at this scale is genuinely new territory. The aircraft pulls data simultaneously from space-based assets, allied platforms, and ground stations, building a live composite picture of the battle space that no single sensor suite could generate alone. The pilot sees more, faster, with better confidence about what's real and what's a decoy or a spoofed return. The Dark Eagle variant, according to what circulates in analyst discussions, trades that networked architecture for something different: full autonomous operation with no external connections required. For missions where transmitting anything is itself a liability, where the network has been jammed or destroyed, or where operating inside an enemy's air defense perimeter means any emission is a targeting cue, you want an aircraft that functions as a closed system. That's a fundamentally different capability from the GCAP baseline, and it requires different avionics design from the ground up. The materials used on the airframe are classified, but open-source defense literature describes radar-absorbent coating characteristics that push beyond what the F-35 currently achieves. Combined with adaptive signature management, the physical and electronic stealth work together rather than compensating for each other's limits. Britain isn't following anyone's lead on this. The Tempest program, and whatever runs beneath it at the classification levels that don't surface in official statements, reflects a country that looked at its specific threat geography, its specific alliance dependencies, and decided to build an answer rather than wait for one. The Dark Eagle name may never appear in an official document. The program it describes almost certainly already exists. Watch the GCAP partnership announcements and the MOD budget anomalies. That's where the real story breaks before it goes public. Somewhere inside a classified hangar, there may already be an aircraft that can reach any city on Earth in under 90 minutes, drop a strike from the edge of space, and land back on a runway before the enemy even confirms what hit them. No government has officially acknowledged it. No journalist has photographed it. And yet China and Iran are restructuring their entire air defense doctrine around the possibility that it's real. That's not speculation dressed up as news. That's the logical conclusion of a pattern that Skunk Works has been running for decades, and it's a pattern worth paying close attention to. What we're talking about is a program that circulated in defense analyst circles under the name Phantom Wing, a black project allegedly developed inside Lockheed's most secretive division, built to operate at the boundary where atmosphere ends and orbit begins, and designed to strike from a domain that no adversary currently has any answer for. By the end of this video, you'll understand exactly why this aircraft, if it exists, doesn't just change the speed of warfare, it changes the entire math adversaries use when they think about confronting the United States. We're going to cover where this program allegedly came from, how orbital strike actually works, why neither China nor Iran can stop it, and what's real versus what's still in the rumor layer. Let's get into it. The SR-71 Blackbird was officially retired in 1998. For 25 years, it held the record as the fastest air-breathing aircraft ever flown, capable of outrunning surface-to-air missiles simply by accelerating away from them. When the Air Force stood those airframes down, the public story was that satellites had made high-speed reconnaissance redundant. Cheaper, safer, no pilot at risk. Lockheed accepted that narrative publicly and kept working privately. That's not a conspiracy framing. That's just what Skunk Works does. The division was built by Kelly Johnson in the 1940s specifically to work outside normal bureaucratic visibility, and every major platform it's produced followed the same arc. Something gets developed in secret, flies operationally for years, and only surfaces publicly when the program has moved far enough along that disclosure, no longer compromises it. The F-117 Nighthawk is the cleanest example. It flew its first operational mission years before the Pentagon acknowledged the aircraft existed. Neighbors near Tonopah Test Range in Nevada were seeing a delta-shaped aircraft in the sky throughout the early 1980s. The official confirmation didn't come until 1988. By that point, the aircraft had already been combat-ready for years. The B-2 Spirit followed the same pattern. The SR-72 followed it too, except in that case, Lockheed themselves broke the silence. In 2013, they published a concept article in Aviation Week describing a hypersonic successor to the Blackbird, targeting Mach 6, built around a combined cycle engine that could handle both subsonic and scramjet regime flight. The reason they disclosed it wasn't because the program was new. It was because the underlying propulsion technology had matured enough that keeping it completely dark was no longer the point. What matters about the SR-72 disclosure is what it implies. Lockheed went public with a Mach 6 reconnaissance and strike aircraft in 2013, which means the development timeline for that system stretches back well before that. And since 2013, Skunk Works has gone almost completely quiet on where that program stands today. That silence is meaningful. The phantom wing concept, as it's circulated among defense analysts and in patent filings tied to advanced propulsion and thermal protection systems, isn't described as a faster version of the SR-72. It's described as a categorically different kind of aircraft, not a hypersonic jet that flies through the upper atmosphere at high speed. Something that climbs above the atmosphere entirely, uses low orbital mechanics to cover distance, and then descends on a target from above at hypersonic velocity during re-entry. That's a different machine. It operates in a different domain, and the defenses that exist to stop conventional aircraft, or even conventional hypersonic missiles, weren't built with this flight profile in mind. To understand why that matters so much, you need to understand what orbital strike actually means mechanically, and why the physics of it are so difficult to defend against. Think about a standard strike mission. An aircraft takes off, flies through the atmosphere at some altitude, crosses into hostile airspace, releases a weapon, and exits. The entire flight path stays inside the same layer of air that weather systems move through. That's the domain every air defense network on Earth is designed to cover. Orbital strike works on completely different geometry. The aircraft climbs steeply after takeoff, burns through the upper atmosphere, and crosses into the region where air is too thin to generate conventional lift. At that altitude, the curvature of the Earth itself becomes the flight path. The aircraft isn't flying over the planet so much as it's arcing around it, using near-orbital mechanics to cover thousands of miles in a fraction of the time any conventional aircraft could manage. Then it pitches down, bleeds velocity through re-entry, and descends on the target from almost directly above. That descent profile is where the 90-minute global reach number comes from. At hypersonic re-entry speeds, the distance between a launch point in the continental United States and a target on the other side of the world stops being measured in hours. It's measured in the time it takes to arc through low orbit and come back down. The physics behind this aren't theoretical. China's DFZF hypersonic glide vehicle uses a related principle. Boost a warhead to extreme altitude and velocity, then let it glide and maneuver during descent rather than following a ballistic arc. The phantom wing concept, as described by analysts tracking the program, takes that same logic and applies it to a reusable crewed or semi-crewed platform. Not a missile you fire once. A vehicle that returns to base, gets serviced, and flies again. Getting there requires solving one of the hardest problems in aerospace engineering: transitioning an aircraft from conventional turbine flight at low speed through the transonic and supersonic regimes all the way to Mach 6 and beyond demands an engine that can function across that entire range without stalling, melting, or losing thrust at the worst possible moment. Scramjet engines only ignite efficiently above roughly Mach 4, which means the propulsion system has to bridge that gap. A combined cycle engine starts as a turbine, accelerates the aircraft to the speed where scramjet combustion becomes viable, then transitions cleanly to hypersonic mode. Lockheed's work on this problem goes back years, and the SR-72 program was built around making that transition reliable enough to be operational rather than experimental. Once the aircraft is above the atmosphere and descending, something interesting happens with stealth. At the speeds involved during re-entry, friction with the upper atmosphere generates a plasma sheath around the airframe. That layer of ionized gas absorbs radar energy rather than reflecting it back to a ground station. Conventional stealth coatings work by shaping the aircraft to scatter radar returns. The plasma effect works by swallowing the signal entirely. The aircraft is, in practical terms, invisible to ground-based radar during the exact phase of flight when it's most dangerous. The X-37B program adds another layer to this. The Air Force's unmanned spaceplane has been flying classified orbital missions for years, with individual sorties lasting many months. The official explanation covers technology demonstration in a general sense, but several defense analysts have noted that the vehicle's flight profile, its re-entry characteristics, and the thermal protection systems it uses are all directly applicable to a crewed or strike-capable successor. Whether the X-37B is a direct ancestor of something like the Phantom Wing, or simply a parallel program solving overlapping problems, the technology it's validating maps cleanly onto what an orbital strike aircraft would need to survive and function. That gets at why China and Iran aren't just watching this program with curiosity. They're watching it with urgency, because the defense gap it creates isn't something either country currently has any real answer to. China's most capable ground-based air defense network is built around systems like the HQ-9 and its naval equivalents. These are serious, modern platforms. They can engage targets at long range, they're mobile, and they're designed to handle multiple threats simultaneously. Against a conventional strike package, they'd cause real problems. The word conventional is doing a lot of work in that sentence. Every air defense system ever fielded is fundamentally a solution to a geometry problem. A radar acquisition system scans a defined volume of airspace, detects a target moving through it, hands off tracking data to a fire control system, and that system calculates an intercept trajectory and launches. The whole chain depends on one assumption, that the threat is coming from a direction and altitude the radar was designed to watch, with enough time in the engagement envelope to actually intercept it. An orbital strike aircraft breaks every variable in that chain at once. The descent profile we covered earlier means the threat arrives from almost directly overhead, not from the horizon where most radar apertures are optimized to look. The angle alone creates a detection problem that no software patch fixes, because it's baked into the physical orientation of the antenna arrays. To cover orbital re-entry angles, you'd need a fundamentally different sensor architecture pointed at the sky rather than the horizon, networked with fire control systems fast enough to generate an intercept solution in an extremely compressed window. That window is roughly 90 seconds or less from initial detection to impact, assuming the radar can acquire the target at all through the plasma sheath effect. 90 seconds is not enough time for any currently fielded intercept system to run a full engagement sequence against a maneuvering hypersonic vehicle descending from near orbital altitude. The missile has to be in the air before the geometry becomes workable, and you can't do that if you don't know the target is coming. Iran's situation is considerably more exposed. Their air defense inventory leans heavily on Russian origin systems, some of which date back decades. These aren't platforms designed to engage targets moving at hypersonic speeds under any geometry, let alone the near-vertical descent profile orbital strike produces. During the strikes attributed to Israel in recent years, Iranian systems struggled to consistently engage much slower, much lower-flying threats. The gap between what they operate and what an orbital strike aircraft represents isn't a gap you close with training or tactics. There's a psychological layer here too, and it matters as much as the technical one. Conventional deterrence works because both sides can see each other's capabilities developing in real time. Satellites track airfield construction, analysts count aircraft tail numbers, intelligence services monitor production rates. That visibility allows adversaries to calibrate their posture. They can assess the threat, build a response, and communicate that response as a deterrent of their own. An aircraft that can loiter in orbit for extended periods and descend without warning removes that visibility entirely. There's no ingress track to detect, no tanker support to monitor, no pre-flight activity to tip off intelligence collection. The first indication that a strike is happening could be the strike itself. Ballistic missiles follow a predictable arc from launch to impact, and that predictability is actually one of their weaknesses from a deterrent standpoint. Terminal defense systems have known intercept geometries to work with. A vehicle that maneuvers during descent on a profile that originates above the atmosphere doesn't give interceptors a predictable arc to solve for. That's not a marginal improvement in survivability. That's operating in a domain where the intercept math doesn't currently exist. So let's be straight about where the line sits between confirmed and alleged, because they're not the same thing, and collapsing them doesn't serve anyone. What's confirmed, the SR-72 program is real, Lockheed said so publicly. Skunk Works operates on black budget funding that's documented in congressional appropriations history. The X-37B is flying right now, somewhere above your head on a mission the Air Force hasn't fully explained. The physics of orbital re-entry and plasma stealth aren't classified. They're published aerospace science. Those things are facts. The Phantom Wing name isn't. The specific capability claims aren't. What circulates in defense analyst communities is a composite assembled from patent filings on advanced thermal protection and combined cycle propulsion, from signals intelligence reporting that's never been officially sourced, and from the kind of inference that happens when people who track black programs for a living notice line items in the Pentagon's budget that don't match anything on the acknowledged aircraft list. That's not nothing. It's also not a confirmed program. Here's why the Pentagon might not mind that ambiguity existing. An adversary that believes this aircraft is already operational has to plan for it. They have to spend money on detection architecture they don't currently have. They have to redesign missile defense doctrine around a threat profile their engineers are still trying to model. They have to absorb the psychological weight of knowing there may be a weapon in their opponent's inventory they have no answer for. All of that happens whether or not the platform has actually completed its first operational flight. Strategic ambiguity isn't a side effect of secrecy. Sometimes it's the product. The budget signal points in one direction. Unacknowledged special access programs have consumed a growing share of U.S. defense spending over the past decade, and the gap between total black budget allocation and the programs analysts can account for by name has widened. Something is absorbing that money. Multiple somethings, probably, and the historical pattern keeps repeating. The F-117 was a rumor, then a fact. The B-2 was a rumor, then a fact. The SR-72 itself was analyst speculation until Lockheed published it. Every one of those programs followed the same arc: denial, silence, then confirmation after the technology was mature enough that disclosure cost nothing strategically. Nobody outside the program knew the truth until Skunk Works decided they could afford to share it. That's exactly where the Phantom Wing sits right now. Either it's already flying and we're in the silence phase, or it's close enough that the rumors are doing useful work in the meantime. Both possibilities produce the same outcome for China and Iran. Whether the Phantom Wing is airborne tonight or still years from its first flight, the gap it represents is already reshaping how adversaries think and spend. China and Iran aren't building next-generation air defenses because they feel secure. On June 4, 2026, a thermal camera near Area 51 recorded something impossible. The aircraft carried no tail, no visible flaps, and no cockpit. Defense analysts immediately linked the shape to America's next-generation fighter program. But the real story isn't the airframe itself. It's the technology that lets a plane turn and climb without moving a single surface. Groom Lake remains the graveyard of secrets for American military aviation. The U-2 spy plane first flew there in the 1950s. The SR-71 Blackbird and the F-117 Nighthawk both spent years in the skies above that same restricted desert basin, long before the public knew they existed. That history meant the defense community paid attention when thermal cameras picked up an unknown shape in early June 2026. The footage first surfaced on June 4th through aviation observers who monitored the restricted airspace around the test range. That imagery showed a single aircraft in night flight, captured in infrared against the cold Nevada desert floor. The shape stood out immediately because it lacked every surface Americans expect to see on a modern fighter jet, from stabilizers to control surfaces, and the wings swept back in a cranked kite planform with two small Canard foreplanes forward of the main wing. Nothing in the current U.S. inventory matches that silhouette. The aviationists published the imagery before most other defense outlets. Their analysis noted that the thermal signature indicated a single airframe under power. The aircraft appeared to be conducting a low-speed pass or a landing approach, which meant it was either a prototype or a full-scale technology demonstrator. And that behavior matters because Black Project aircraft rarely fly in conditions where amateur sensors can capture them. For decades, sightings like this have preceded every major black project reveal. The U-2 created the original UFO wave over the desert in 1955, and the F-117 generated thousands of false reports before the government declassified its existence. Yet the pattern remains unmistakable, and it has repeated with nearly every secret aircraft that America has ever tested. When something unknown flies over Area 51, the rest of the world usually finds out about it 5 to 10 years later. The shape caught on thermal footage isn't random. It's a tailless, cranked kite wing with forward canards, a configuration that defense analysts immediately recognized and linked to the Boeing F-47. President Trump announced that aircraft on March 21, 2025. The F-47 will replace the F-22 Raptor, and it's the first sixth-generation fighter program ever to reach the engineering and manufacturing development phase. Boeing won the contract after years of secret competition against Lockheed Martin. The aircraft will carry advanced stealth, artificial intelligence-assisted combat systems, and the ability to command autonomous drone wingmen. Yet the shape in the Nevada sky raised an immediate problem. Canards are small control surfaces mounted ahead of the main wing. They improve maneuverability and low-speed handling, but they create frontal radar reflections that most stealth engineers try to eliminate. The F-22 and the F-35 both avoid canards for exactly that reason, which explains why analysts were surprised to see them on a Black Project test article, and either the stealth technology has advanced beyond the need for pure shape optimization, or the aircraft in the footage isn't the final F-47 design configuration. Both possibilities point to a different breakthrough, and that's where the real story begins. The war zone warned that many questions remain. The outlet warned that the aircraft could be a subscale demonstrator, a full-scale mock-up, or an early prototype that will change shape before it enters active production. Until Boeing or the Air Force releases an official image, every analysis remains educated speculation. Yet the F-47 might not be the only program flying over Nevada. Since 2020, DARPA has been running a separate initiative that remains just as radical, and it's called CRANE, which stands for Control of Revolutionary Aircraft with Novel Effectors. The goal isn't to build a fighter, it's to prove an aircraft can fly and maneuver without any moving external surfaces. Aurora Flight Sciences, a Boeing subsidiary, won the contract to build the demonstrator. The aircraft carries the designation X-65, and it's subsonic, unmanned, and weighs over 7,000 pounds with a 30-foot wingspan that makes it smaller than most tactical jets, but large enough to test full-scale aerodynamic principles. Every number in that description looks modest, which means the real surprise comes from what designers built the X-65 to do. It'll turn, climb, and descend using a system that has no flaps, no rudders, and no ailerons. DARPA spent $38.2 million on the program in fiscal year 2024, and another $23.8 million in fiscal year 2025, which means the total visible investment sits at over $60 million. That isn't a classified black budget. That's less than one F-35, and it could change how every future aircraft is built. Aurora hasn't hidden the X-65 in a vault because the company published photographs of the airframe under assembly, and the program is real, it's funded, and 2027 marks the first flight. Yet few people outside the defense industry have ever heard of it. This isn't a conspiracy theory. It's a DARPA program with a public budget and a named contractor, and it's preparing for a first flight in 2027 that will test something no previous aircraft has ever attempted before. In 1903, the Wright brothers flew at Kitty Hawk, and every powered aircraft since then has used the same method to turn and control its flight, from the wing warping of the first flyer to modern flaps and ailerons. Those surfaces physically move to redirect airflow and change the aircraft's attitude, a principle that has governed aviation for over 120 years. The X-65 does none of that. Instead, the demonstrator uses a technology called active flow control. It relies on 14 banks of fixed actuators embedded in the wing and tail surfaces, and each bank blasts precise jets of air that create lift and directional forces. Think of it like steering a boat with water jets instead of a traditional rudder, because the hull stays fixed while the thrust changes direction. That's exactly how the X-65 will steer without rudders or flaps when it flies for the first time in 2027. The 14 actuator banks aren't placed randomly. They're positioned at specific points across the wing where airflow separation normally occurs during high-angle maneuvering, and by blasting air at those locations, the X-65 can create differential lift to produce roll, increase drag to yaw, or adjust camber to pitch up and down. All of this happens with fixed hardware. None of that is theoretical. DARPA and Aurora tested scaled models in wind tunnels before full-scale construction, and the fixed actuators weigh less than the hydraulic systems they replace. They remove every seam and gap that opens when a conventional flap extends, and on a stealth aircraft, those gaps become radar reflection points that an enemy sensor can exploit during takeoff, landing, or combat maneuvering. Active flow control turns on or off as needed. It adds energy to the airflow in a regulated manner that replaces the mechanical complexity of movable surfaces and leaves the aircraft with fewer parts to maintain and a lighter airframe overall. The catch is that the system requires pressurized air, which demands engine power and sophisticated control software. But DARPA has already solved harder problems with less funding. If the X-65 proves the concept in operational flight testing, the technology can scale to larger aircraft that operate in contested airspace without the stealth penalties of traditional moving parts. The advantages go beyond maintenance. On a conventional stealth fighter, the pilot controls the aircraft by extending flaps, rudders, and ailerons, and every time one of those surfaces moves, it opens a gap in the airframe that reflects radar energy. It's a temporary breach in the aircraft's invisible cloak that happens during combat maneuvering, takeoff, and landing. A surface-free aircraft doesn't have that problem. The outer mold line stays exactly the same during a gentle turn or a hard evasive pull, because there are no hinges to flex and no edges for enemy radar, and the radar cross-section remains consistent across the entire flight envelope, which is something no current operational fighter can promise. That consistency explains why a tailless, surface-free design appeals to engineers who want to push stealth beyond current coatings and shaping. That leads to how modern stealth actually works, because both techniques work well when the aircraft is in straight and level flight. But the moment a pilot banks hard or deploys landing gear, the geometry changes and the signature spikes in ways that ground-based radar can exploit. Active flow control removes that variable entirely because the outer surface never changes shape. That's the ghost advantage. The aircraft never exposes itself because it never changes shape. The weight savings are also real. Hydraulic actuators and backup mechanical systems add hundreds of pounds to a fighter's empty weight, and removing them frees up mass for fuel, weapons, or sensors that increase lethality without increasing radar signature. The X-65 is only a subsonic demonstrator, but the physics scale. A full-scale 6th-generation fighter that uses active flow control could operate at longer range, carry heavier payloads, and survive in airspace that would force a conventional aircraft to run its control surfaces wide open. The path from DARPA experiment to operational black project has been traveled many times. The U-2 started as an experimental reconnaissance concept before it became the CIA's highest altitude spy plane. And the F-117 began as Have Blue, a technology demonstrator that proved stealth shaping could work. Have Blue crashed twice, but the data it generated led directly to the F-117 production line. The RQ-170 Sentinel flew for years in secret before anyone outside the Pentagon knew. And in every case, engineers tested the technology openly before it disappeared into classified programs. And that points to the timeline, because Aurora plans the first X-65 flight for 2027. But the Area 51 sighting happened in 2026, which means that 1-year gap rules out nothing. Black project history shows that the most important flights stay off public schedules. DARPA programs often spawn operational test articles that fly years ahead of the acknowledged schedule. And if the X-65 technology has matured faster than public timelines suggest, the aircraft over Nevada could be an integrated test bed, combining this technology with a larger combat airframe. That leads to what the F-47 is actually supposed to do, because the Air Force expects the F-47 to operate as a command node for collaborative combat aircraft, which are autonomous drone wingmen that carry weapons and sensors under a crewed leader. A tailless, surface-free design fits that role perfectly. It could penetrate contested airspace without the radar spikes of a conventional fighter, direct multiple drones simultaneously, and return without ever exposing the control surfaces that betray most stealth platforms. Boeing hasn't confirmed the F-47 uses this system, and DARPA doesn't discuss operational transitions. That isn't confirmed, but it's exactly what you'd build if you had the technology and the budget to field a next-generation combat aircraft that could dominate contested airspace without relying on conventional moving surfaces. The United States isn't the only country building a sixth-generation fighter. China has been flight testing its own design for years, and Russia has announced plans to field a successor to the Su-57, which means both programs aim to close the gap that American stealth technology opened in the 1990s. Neither country has confirmed it's testing the same approach, which means the technology stays an American advantage only if engineers mature it first, and that creates the problem. In 2011, Boeing built its last F-22 Raptor after only 187 aircraft, and that number remains so small that senior Air Force officers call it a strategic liability. 187 aircraft isn't a fleet, and it's a liability that still wears stealth coatings. The F-35 Lightning II is a capable multi-role fighter, but designers didn't build it to win air superiority battles against peer adversaries, because it's a workhorse and not a thoroughbred. That leads to why the F-47 matters. America needs the F-47 to restore the edge. Active flow control isn't a minor upgrade because it's a qualitative change in what an aircraft can do, and a fighter that never changes shape can survive longer in denied airspace and coordinate with autonomous wingmen without exposing itself. Reverse engineering that capability would require an adversary to replicate the embedded actuator software and the thousands of hours of flight test data needed to make it reliable. China has been flight testing its own next-generation design for years. The program appears to be building toward an operational sixth-generation fighter that could enter service by the early 2030s, and that timeline pressures the American programs. If the F-47 program slips, or if active flow control fails to transition from the X-65 to an operational platform, the United States could find itself with a numerical and technological disadvantage in the Pacific. The Ghost Jet isn't science fiction. It's the next era of American air power being written in Nevada desert air. America's secret Ghost Jet may soon appear on the USS Gerald Ford, shocking Pentagon officials and rivals. This tailless, triangle-shaped fighter boasts smart skin sensors, laser weapons, and hypersonic speeds of over 6,000 miles per hour. It can even command a swarm of robotic wingmen. Earlier stealth jets seem obsolete in comparison. Has the U.S. Navy just rewritten the rules of aerial warfare? And how will China and Russia react to this invisible predator of the skies? Join us as we unveil the seventh-generation fighter jet before it makes it on the United States aircraft carrier. The sky above the USS Gerald Ford lit up with a bright blue flash as something incredible took place. After nearly a century of struggle, the United States Navy had finally solved one of its biggest challenges. Carrier-based jets could now match or even surpass land-based fighters. For years, aircraft carriers had a major disadvantage. Their jets had to be smaller, lighter, and carry less fuel compared to those launching from land. As countries like China and Russia built powerful land-based fighters and long-range missiles, many experts doubted whether carriers could hold their ground in modern warfare. That changed with the Navy's next-generation air dominance fighter. Unlike the older FA-18 Super Hornets, this new jet brought futuristic technology that had once seemed impossible. It wasn't just a single aircraft, it was the leader of a small team. Each NGAD fighter was paired with autonomous drones, commonly called collaborative combat aircraft. These drones carried extra weapons, sensors, and fuel, following the lead fighter's commands while also making quick decisions on their own. A single pilot could now manage what used to take several people. The USS Gerald Ford's firepower grew even stronger with the addition of the Helios laser weapon system. This powerful 150-kilowatt laser could track and destroy incoming missiles and enemy drones almost instantly. Unlike traditional missiles that could run out, the laser remained operational as long as the ship had power. Most people had no idea how fast this technology was advancing. When an Air Force official revealed in 2020 that a test version of the NGAD fighter had already flown, defense experts were caught off guard. The Navy had been quietly working on this breakthrough for more than 7 years, replacing outdated systems from the 1990s with cutting-edge technology designed for the future. The USS Gerald Ford was designed with cutting-edge advancements in mind. As the Navy's most sophisticated aircraft carrier, it featured electromagnetic catapults that propelled aircraft more swiftly and effectively than traditional steam-powered systems. Its nuclear reactors generated the vast energy required for the Helios laser. The NGAD fighter also looked completely different from older jets. It had no vertical tail fins and featured a sleek triangular design, allowing it to fly in ways that would have made traditional aircraft lose control. Advanced computer systems made thousands of tiny adjustments every second to keep it steady and maneuverable. In training exercises, the results spoke for themselves. Against experienced pilots flying F-35s, the NGAD fighter and its robotic wingmen won nearly every simulated battle. The difference was overwhelming. For countries that had spent billions developing anti-ship missiles to keep United States carriers at a distance, this presented a serious problem. With these new jets, carriers could now operate much closer to enemy territory without fear. For the first time since World War II, carrier-based jets weren't just keeping up with land-based fighters, they were better. This wasn't just an upgrade. As the sun set behind the carrier, the new fighter launched into the night, its silhouette blending into the sky. The aircraft represented a development in naval warfare. What happens when these advanced fighters go beyond the clouds and into the vast darkness of space? Could the next generation of American warplanes be used as spacecraft? Engineers across America are already working on technologies beyond those used on the USS Gerald Ford. While naval aviation advances, the next leap is happening in secret labs. The goal isn't just faster planes, it's aircraft that can move between air and space. These next-generation hypersonic fighters could transform aerial combat. Traveling above Mach 5, more than 6,000 kilometers per hour, they could cross continents in minutes. A fighter this fast could fly from New York to Los Angeles in under 30 minutes, making it nearly impossible to track, let alone stop. Building such an aircraft comes with massive challenges. At extreme speeds, air friction generates heat strong enough to melt standard materials. To solve this, the Air Force and NASA are developing heat-resistant composites that can withstand over 2,000 degrees Celsius without breaking apart. Propulsion is another hurdle. Regular jet engines can't function well at extreme speeds or in the thin upper atmosphere. That's where scramjets come in. Unlike traditional engines, scramjets have no moving parts. They use the aircraft's speed to compress incoming air, generating thrust. Since 2018, the Air Force's Mayhem project has been testing scramjet prototypes, gradually improving their performance. Unlike earlier fighter jets, these advanced aircraft wouldn't just fly high, they could briefly leave Earth's atmosphere. By reaching altitudes above 100 kilometers, they could enter a suborbital path, skipping across the upper atmosphere like a stone across water. This would allow them to strike targets with almost no warning, conduct surveillance from altitudes beyond the reach of anti-aircraft weapons, and even deploy small satellites to restore communications in combat zones. The United States military has been quietly funding this research for years. DARPA has been working on airspace transition vehicles since 2020, focusing on designs that can move between the atmosphere and space without rockets or launch pads. But breaking into space creates new risks. Outside Earth's atmosphere, cosmic radiation can damage electronics and pose health risks to pilots. Engineers are developing shielding and radiation-resistant computer systems to keep these aircraft safe. Fuel is another challenge. Traditional jets can refuel mid-air, but space-capable aircraft need an energy source powerful enough to push them beyond most of Earth's gravity and still bring them back safely. Advanced hydrogen propulsion is one possible solution, providing high energy output with only water as a byproduct. The race to develop this technology is already underway. China is rapidly increasing its hypersonic research budget, while Russia's PAKDP program is working on similar aircraft. Any country that masters space-capable fighters will gain a major military advantage. This also raises legal questions. The 1967 Outer Space Treaty, bans nuclear weapons in space, but doesn't address conventional weapons or temporary military operations beyond Earth's atmosphere. This loophole has sparked new debates at the United Nations about the future of space warfare. Even the best pilots would need entirely new training for these aircraft. At hypersonic speeds, decisions must be made in milliseconds, too fast for human reaction times. AI assistance and augmented reality systems would have to predict and respond to problems before they happen. The Air Force is already preparing for this future. Specialized bases are being upgraded to support these hybrid airspace vehicles, with reinforced hangars, advanced cooling systems, and specialized fuel storage facilities built to handle the extreme demands of hypersonic flight. While sixth-generation fighters represent the future of modern warfare, these seventh-generation space fighters are something entirely different. The line between science fiction and military reality is disappearing fast. What once seemed impossible is now just a matter of time. As these jets push the limits of technology, the big question is, who or what will be in the pilot's seat? Behind closed doors in high-tech labs across America, engineers have been building the brains of future warplanes long before a single piece of metal is cut. Before these next-generation fighters take shape, their artificial intelligence is already training in virtual battles against the world's best pilots. AI is no longer just a co-pilot, it is being designed to take over entirely. What began as basic autopilot and warning systems soon expanded to flight guidance and real-time threat analysis. Now, cutting-edge AI can autonomously execute complex combat missions, making split-second decisions faster than any human pilot. A breakthrough came with the Pentagon's Project Maven. Launched in 2017, it began by teaching AI to recognize objects in drone footage. Over time, the system evolved to track multiple moving targets, even through clouds, smoke, and electronic interference. The next generation of warplanes will look unlike anything seen before. There will be no cockpits or instrument panels, just advanced processors, cooling systems, and AI-powered decision-making packed inside a sleek, high-speed airframe. These aircraft will be more like flying supercomputers than traditional jets, controlling weapons, sensors, and engines with machine intelligence. The way these planes are built is also changing. In factories across Nevada and California, massive 3D metal printers are already shaping experimental aircraft parts. These machines create complex designs layer by layer, using titanium and carbon fiber, making structures that were previously impossible with older manufacturing methods. This advancement accelerates production at an unprecedented rate. In the past, developing and testing a new design could take several years, involving extensive prototyping, manual adjustments, and countless trial and error phases. Now, with advanced automation and AI-driven simulations, the entire process can be streamlined, reducing development time to just weeks. Engineers can rapidly iterate designs, test performance in virtual environments, and refine prototypes with real-time data, allowing for faster innovation and deployment. Engineers feed designs into simulations where AI runs countless virtual test flights, refining the aircraft before a real one is built. Only the best designs move forward, ensuring each new fighter is an improvement over the last. Military planners see an opportunity in this rapid development cycle. Instead of producing hundreds of identical jets that risk becoming outdated, they can create smaller batches that evolve over time. Each generation learns from the last, making the fleet smarter and more adaptable. Another breakthrough is the concept of smart skin. Instead of mounting separate radar and sensors, the entire surface of these aircraft will be covered in tiny sensors, turning the whole plane into a flying surveillance system. Traditional jets have blind spots, these will have none, detecting threats from all directions and instantly sharing that data with other AI-powered aircraft. This real-time connection gives AI-controlled jets a major edge. Multiple fighters can operate as a single intelligent unit, responding to threats as a team. Smaller, unmanned drone fighters, built at a fraction of the cost, can fly alongside, carrying extra weapons, scouting ahead, or even sacrificing themselves to protect the primary aircraft. But with AI-driven warfare, ethical concerns grow. Military rules state that a human must have meaningful control over combat decisions. Yet at hypersonic speeds, human reaction time simply cannot match AI decision-making measured in microseconds. The Navy has formed an advisory board to address these concerns, ensuring AI follows rules of engagement and minimizes unnecessary harm. However, programming a machine to understand restraint and proportionality remains an unsolved challenge. Technical hurdles also remain. AI-driven aircraft require immense computing power, generating extreme heat. Scientists are exploring quantum computing and advanced cooling systems to keep these machines running efficiently. And while AI has mastered strategy games like chess, aerial combat is far more unpredictable. Training AI pilots in massive simulation environments is key to sharpening their combat skills. The combination of rapid manufacturing and AI autonomy is reshaping aerial warfare. The nation that perfects this technology first will gain an overwhelming advantage, one where warplanes don't just fly, but learn, adapt, and improve with every mission. Even the most advanced fighter jet loses its edge if the enemy spots it from miles away. But what if these new warplanes could completely disappear even from human sight? The most surprising thing about the next generation of fighter jets isn't what they have, it's what they don't. The familiar vertical tails that have defined military aircraft for over a century are gone. Sharp edges and visible engine intakes are missing too. Instead, these jets have a smooth, flowing shape that looks strange to experienced pilots. With soft edges and no clear front or back from certain angles, the design defies traditional aerodynamics and stability rules. It resembles a flying triangle more than a conventional aircraft. This groundbreaking transformation is the result of decades of advancements in stealth technology. The first-generation stealth aircraft, such as the F-117 Nighthawk, relied on angular surfaces to scatter radar signals. The B-2 Spirit bomber improved upon this by incorporating smooth curved contours to further reduce detectability. Today, the most advanced designs push the boundaries even further, striving for near-total invisibility to enemy radar systems. Older planes needed vertical tails for stability, but those tails made them easy radar targets. Engineers replaced them with an advanced flow control system originally tested on the B-2. Instead of stabilizers, hundreds of tiny airjets adjust the aircraft's balance in real time. A computer makes constant corrections, ensuring smooth flight without traditional control surfaces. The aircraft's skin also enhances stealth. Radar-absorbing materials are built directly into the structure, making them more durable than older coatings that wore off. Some sections even contain carbon nanotube layers that absorb radar signals and release the energy as harmless heat. Heat detection is another challenge. Fighter jet engines produce extreme heat, making them easy targets for infrared sensors. New designs cool the exhaust before it leaves the aircraft, then spread the remaining heat over a wider area, reducing their infrared signature. This makes it harder for heat-seeking missiles to lock on. Beyond stealth, these jets are built for adaptability. Older fighters were rigidly designed, meaning upgrading one system often required redesigning the entire aircraft. The new generation features modular components, allowing engineers to swap out weapons, sensors, and avionics quickly without major overhauls. This approach cuts costs and extends the aircraft's lifespan. Instead of waiting years for a completely new model, militaries can upgrade existing jets in weeks. Experts estimate this could reduce costs by 30 to 40% compared to today's most advanced fighters. For radar operators, detecting these aircraft is becoming nearly impossible. Older stealth jets had radar signatures the size of a small bird. Today's fighters appear smaller than a marble. The goal is to become virtually invisible to radar altogether. Even spotting these jets with the naked eye is difficult. Adaptive camouflage panels on their surface can change color to blend with the sky or terrain below. While not true invisibility, this makes them extremely hard to track visually, especially from a distance. Every aspect of these jets is built for real-world combat. Critical areas are reinforced to withstand damage, maintenance access points are easier to reach, and vital systems have built-in backups. These improvements come directly from lessons learned in modern warfare. Stealth technology has always been a cat-and-mouse game. As enemy sensors evolve, stealth aircraft must adapt. With flexible designs and cutting-edge technology, these new jets are built to stay ahead, ensuring dominance in future battles. As America leads in stealth tech, others race to catch up. How did a marketing move spark a trillion-dollar power struggle? The idea of fighter jet generations didn't start with military strategists or aviation pioneers. It was a marketing move by Lockheed Martin. In the early 2000s, the company needed a way to make its new F-35 fighter stand out. The solution they came up with was to call it fifth generation, making everything else seem outdated. The term caught on. Soon, military officials, journalists, and analysts worldwide adopted the classification. Older jets were retroactively sorted into generations. The Korean War-era F-86 Sabre became first generation. The Vietnam-era F-4 Phantom was third generation, and Europe's Eurofighter Typhoon landed in the fourth generation category. What began as a sales tactic reshaped global defense strategy. Countries now felt pressured to keep up. When China unveiled its J-20 in 2011, state media repeatedly emphasized one point. It was China's first fifth-generation fighter. The message was clear. China had joined an exclusive club previously limited to the United States and Russia. India accelerated its fifth-generation program. Japan prioritized acquiring such capabilities. South Korea launched an ambitious effort to build its own next-generation fighter instead of buying from abroad. This marketing-driven shift overlooked an important fact. Before generational labels took hold, countries evaluated fighters by their capabilities, not arbitrary classifications. The French Rafale and Swedish Gripen featured advanced technologies that rivaled early fifth-generation jets. Yet they were dismissed as merely 4.5 generation. The United States officially moved towards sixth-generation fighters in 2014 with DARPA's Air Dominance Initiative, securing nearly $1 billion in early funding. By 2020, the Air Force confirmed that a demonstrator had already flown successfully, pushing rivals to accelerate their programs. China responded by reorganizing its aerospace sector, pouring funds into AI and advanced materials research. Satellite images soon revealed remote test sites where experimental aircraft could fly unobserved. Despite economic struggles, Russia pressed forward with its PAKDP program to replace the aging MiG-31. Officials highlighted its planned ability to operate at extreme altitudes, an apparent counter to United States' interest in space-capable fighters. European nations, unable to match these investments alone, formed cooperative ventures. The UK-led Tempest project partnered with Italy and Sweden, while France, Germany, and Spain joined forces on the Future Combat Air System. Both programs aim to maintain European defense independence rather than rely on American jets. Historically, new fighter generations emerge every 10 to 15 years. Now, the leap from fifth to sixth generation may take 25 to 30 years due to rising costs and complexity. Seventh-generation concepts might not enter service until the 2070s, marking the longest development cycle in fighter history. Meanwhile, the B-52 bomber offers a different approach. First deployed in 1955, it has been continuously upgraded and could serve for a century, proving that evolution sometimes beats revolution. Lockheed Martin, which started this generational race, continues teasing the future. At its Skunk Works 80th anniversary, a mystery aircraft appeared alongside historic designs like the U-2 and SR-71, potentially America's next fighter. With future programs expected to cost hundreds of billions, international collaboration is now essential. What began as a marketing ploy has reshaped global military aviation, making generational labels a defining factor in national security and defense spending. The F-35 is not the most advanced fighter jet the United States has. Neither is the F-22. Those aircraft are what the public is allowed to know about, and there's a difference between those two things that most people never stop to think about. Right now, something called the F-66 is allegedly being tested at a facility that doesn't appear on any official map, with a propulsion system that has nothing to do with burning jet fuel. The reported price tag is $3.2 billion per unit, not $3 billion, not 3.5. 3.2, the kind of specific number that doesn't come from a guess. By the end of this video, you'll understand what that designation means, why that price makes sense, and why the propulsion concept behind this aircraft isn't science fiction. It's classified science. The next window for air dominance isn't opening. It may already be closing, and the countries that aren't flying something like this won't know it until it's too late to catch up. Start with how the numbering actually works. Military aircraft designations in the US don't just count upward in a straight line. The F-22 and F-35 exist in the same generational bracket. Both fifth generation, both developed through programs that went through Congress, both funded through budget lines that lobbyists, contractors, and foreign governments could track if they looked hard enough. When a designation jumps to F-66, that's not an upgrade. That's a separate pipeline entirely. Programs developed at that classification level don't go through the standard acquisition process. They get funded through what's commonly called the black budget, spending that gets approved in broad strokes without line-item transparency. The SR-71 Blackbird operated for years before the public knew it existed. The F-117 Nighthawk flew combat missions before it was officially acknowledged. The B-2 Spirit was deep into development before a single contractor outside the cleared program could confirm it was real. The F-66 designation, if it's genuine, fits that exact pattern. The TR-3B is worth mentioning here because it set a precedent that defense researchers still reference. For years, it was treated as fringe speculation, a triangular craft with alleged non-conventional propulsion, spotted repeatedly near military test ranges. The US government never confirmed it. They also never explained what people were seeing. That's a specific kind of non-denial that shows up around programs the government wants to neither validate nor kill off entirely, because killing it off means explaining why. The $3.2 billion figure works the same way. Round numbers are estimates. Specific numbers come from somewhere. A procurement document, a cleared contractor's internal budget, or a deliberate release designed to let adversaries know a capability exists without telling them what it does. Either way, someone with access to real information put that number into circulation. That's not nothing. Area 51's Groom Lake facility isn't a Cold War relic people visit on tourist maps. The restricted airspace around it is still enforced with live intercept protocols, meaning aircraft that stray too close don't just get a radio warning, they get a fighter on their wing within minutes. That level of active enforcement costs money and requires ongoing authorization. You don't maintain that infrastructure for a museum. So what does 7th generation actually mean in practical terms? It's not just a stealth upgrade over the F-22. 6th-gen programs like the Next Generation Air Dominance platform are already pushing sensor fusion, where the aircraft aggregates data from satellites, drones, and ground stations in real time and presents the pilot with a unified tactical picture instead of raw feeds. 7th generation takes that further. Autonomous teaming with loyal wingman drones, propulsion that operates outside conventional thermodynamic limits, and a sensor suite that turns the aircraft into a mobile intelligence node as much as a weapons platform. The propulsion part is where the F-66 concept breaks from everything in that progression. Every aircraft mentioned so far, the F-22, the F-35, whatever 6th-gen platform eventually gets a name, runs on the same fundamental principle: burn fuel, expand gas, generate thrust. The Brayton cycle. It's been the basis of jet propulsion since the 1940s. The F-66 reportedly doesn't use it, and that's exactly where this stops sounding like an incremental program and starts sounding like something built from a completely different set of assumptions about how flight works. So let's talk about what's actually powering this thing, because this is where the F-66 concept separates itself from every other classified program in the conversation. Every fighter jet flying today, the F-22, the Su-57, the Eurofighter, everything, moves through the air the same way. You compress air, mix it with fuel, ignite it, and the expanding gas pushes the aircraft forward. That's the Brayton cycle, and it's been the ceiling of propulsion engineering for 8 decades. Engineers have gotten extraordinary at working within it, but no one has broken out of it. Not publicly, anyway. Mercury vortex propulsion starts from a different question entirely. Instead of asking how to generate more thrust from combustion, it asks what happens when you spin ionized mercury at extreme rotational velocities inside a contained ring. The physics aren't invented. Ionized mercury and rotating plasma both have documented electromagnetic behavior, and researchers working in magnetohydrodynamics have explored what happens when you push those properties to their limits. The energy interactions get strange at high enough rotation speeds. mass behavior starts to deviate from what classical mechanics predicts. That's the theoretical foundation the TR-3B concept was built on, and it's the same foundation the F-66 allegedly builds further. The TR-3B, as reported by people who claimed access to the program, used a rotating mercury plasma ring to reduce the craft's inertial mass, not its physical weight, but its resistance to acceleration and directional change. Conventional thrusters could then move that craft with a fraction of the energy a normal aircraft would require, because you'd already taken most of the inertia out of the equation. The F-66 concept takes that further. What's being described isn't a thruster that reduces inertia as a side effect. It's a system where manipulating the local gravitational gradient around the aircraft is the primary function. The craft doesn't fight gravity and it doesn't ignore it. It reshapes the gravitational field it's sitting inside, which changes how mass and inertia behave for everything within that field envelope. The aircraft's physical mass doesn't change. What changes is how much energy the universe requires to move it. In engineering terms, that shifts every performance calculation you'd normally apply to an aircraft. G-force limits exist because the human body and the airframe experience force as a product of mass times acceleration. Reduce effective inertia, and you reduce the force generated by any given maneuver. A craft operating inside a reduced inertia envelope can execute direction changes at speeds that would destroy a conventional airframe and kill any pilot inside it. At some point, the limiting factor isn't the airframe at all. It's whether a human pilot can stay conscious long enough to be useful, which is exactly why autonomous systems become central to a platform like this, rather than optional additions. DARPA has spent real money on non-conventional propulsion research, and the Advanced Aerospace Threat Identification Program investigated propulsion anomalies specifically, not as fringe curiosity, but as a national security question, because the UAP phenomena feeding into that program included objects displaying acceleration profiles that no known propulsion system could produce. The program's conclusion wasn't that the physics was impossible, it was that more research was needed, which in classified government language means the door stayed open. None of this is confirmation that the F-66 exists or that mercury vortex propulsion has been successfully engineered into a flyable aircraft. What it means is that the theoretical scaffolding isn't hollow. The physics points somewhere real, and the question isn't whether anyone is working it, it's how far along that work actually is. If the propulsion system is what the reports suggest, the airframe built around it would look nothing like any fighter currently in service. And the design choices that follow from it are exactly as strange as you'd expect. A mercury vortex core sitting at the center of an aircraft doesn't just change how it moves. It changes where the mass is, how the aircraft wants to orient itself, and what happens when you try to control it with surfaces designed around conventional aerodynamics. Traditional control surfaces, rudders, elevators, ailerons, all work by deflecting airflow to rotate the aircraft around its center of mass. Shift that center of mass dynamically, the way a spinning plasma ring would, and those surfaces stop being primary controls. They become backup systems at best and dead weight at worst. That's why the F-66 design reportedly abandons vertical stabilizers entirely and uses a flying wing configuration, no tail, no fins. Just a single continuous lifting surface with flight control managed through the propulsion system itself, rather than external geometry. Flying wing designs aren't new. The B-2 Spirit proved the configuration works, and it's been operational since the 1990s. But the B-2 flies at subsonic and transonic speeds, where airflow behaves predictably and the flight control computers have enough reaction time to keep the unstable airframe from departing controlled flight. A gravitic flying wing pushing hypersonic speeds inside a reduced inertia envelope is a different problem entirely. The aerodynamic forces change character at those speeds, the control margins compress, and any instability that develops does so faster than human reflexes can address. You're not flying it with a stick. You're flying it with software that's reacting in microseconds, and the software has to understand a flight regime that's never been modeled before because no aircraft has ever operated inside one. The stealth profile follows from the same propulsion logic. The F-22's low radar cross-section comes from passive shaping. angles and materials that scatter and absorb radar waves instead of reflecting them back to the source. That's still a fundamentally passive approach, and radar technology has been slowly closing the gap on passive stealth for years. What the F-66 concept introduces is active radar management. A craft generating its own electromagnetic field as part of its propulsion cycle can theoretically tune that field to absorb incoming radar energy rather than scatter it. The aircraft doesn't just look small on radar, it can look like nothing, because it's pulling the signal in rather than deflecting it. Groom Lake was built for programs that don't fit anywhere else. The main runway there stretches well past what any conventional aircraft needs, long enough to accommodate vehicles with unconventional approach speeds and landing characteristics. The restricted airspace extends outward in geometry that gives test aircraft room to run performance profiles without ever leaving controlled airspace. That infrastructure wasn't designed for the aircraft of the 1960s and 1970s. It was designed for whatever came after, and whoever built it clearly expected that something would. Recent satellite imagery from observers tracking the facility shows new hangar structures along the northern edge of the complex and a boundary extension on the eastern restricted zone that happened quietly over the past several years. Neither change has been officially explained. Hangar expansions at Groom Lake don't happen for storage. They happen when something arrives that requires specialized ground handling, temperature-controlled bays, containment systems for materials that aren't safe around standard ground crews, or support equipment sized for an aircraft with dimensions that don't match anything in the public inventory. The $3.2 billion per unit figure starts making sense when you map it against those requirements. Mercury-based fuel systems need containment and handling infrastructure that jet fuel lines can't support. The sensor suite on a platform this far outside normal flight parameters would need custom hardware with no commercial equivalent. Add the ground support, the specialized personnel, and the security infrastructure around a program at that classification level, and $3.2 billion isn't excessive. It might even be conservative. Testing in secret solves one problem. What to do with the secret once testing succeeds? That's a completely different calculation. The timing of whatever is happening at Groom Lake isn't coincidental. China's J-36 and J-50 programs have both produced publicly observable airframe prototypes with sixth-generation geometry, blended flying wing configurations, no vertical stabilizers, sensor apertures distributed across the fuselage skin. Those aircraft aren't operational yet, but the fact that China is flying them in daylight in front of cameras means the development timeline is far enough along that concealment stopped being the priority. Beijing is sending a message about where its program sits, and Washington has to decide how to answer. A gravitic propulsion platform doesn't answer that message by winning a dogfight. It answers it by making the entire framework of contested airspace irrelevant. Air interdiction right now is built around the assumption that even a very stealthy aircraft has to operate within certain physical constraints. Speed limits set by aerodynamics, maneuver limits set by G-force, detection risks that accumulate over time in a defended zone. An aircraft operating inside a reduced inertia envelope with active electromagnetic stealth doesn't share those constraints. Defended airspace that would stop the F-22 or the B-21 cold might not register the F-66 at all. That's not just a tactical advantage, it's a structural one, and it holds even against asymmetric threats. Iran's drone and missile programs have shown that you can saturate conventional air defenses through volume. Enough cheap systems launch simultaneously to overwhelm intercept capacity. A platform with the F-66's alleged performance profile doesn't try to intercept that swarm after launch. It reaches the source before the launch happens. Through airspace, the defending side never saw it enter. The disclosure question follows from all of this. Historically, the U.S. has declassified black programs when keeping them secret costs more than the strategic value of the secret itself. The SR-71 became public partly because the program was maturing and partly because the Soviets already knew roughly what it could do. A controlled leak serves a different purpose. It lets adversaries understand a capability exists without revealing the operational details that make it work. The $3.2 billion figure in the F-66 designation circulating in defense research circles right now may be doing exactly that job. Not a mistake, a signal. Whether the F-66 is already flying test profiles over the Nevada desert or still years from its first sortie, the physics underneath it are real enough that every serious aerospace program on the planet is working some version of the same problem. The race isn't coming, it's already running. Subscribe and drop a comment. What do you think is actually inside those new hangars at Groom Lake right now?